Black holes. I don't know what people see in them. Exit signs? They're on their way out.
The Interplanetary Podcast. The exploration of space for the benefit of all mankind. Your hosts here in London, Matthew Russell and Jamie Franklin.
Oh yeah, baby Vine.
Black holes.
Oh, yeah, black holes definitely should have been in there.
They were a Tim Vine joke.
So why not start with a joke?
What's your favourite Tim Vine joke?
I don't know off the top of my head.
Mine is, I sold my vacuum cleaner the other day. It had just been round the house gathering dust.
That's good. And actually, Matt, very apt, because what else gathers dust?
What else sucks?
A supermassive black hole. Do you realise how hard it's going to be to not start talking about this? So let's just get through. Anything else is just irrelevant to me this week.
Okay. What a week of science and space. It's just unbelievable.
Big time.
But the great thing is, Jamie, I spoke to Ethan Siegel, who's one of my favourite space bloggers.
Yeah, I couldn't make this. You said it was great.
Amazing. We talked about this imminent black hole photograph. So it's a little bit dated because we did it on Tuesday, but nevertheless, you'll see just how amazing this whole thing is.
I can't wait to hear it myself.
Shall we just bang on with this show, Jamie?
Let's dive straight in.
Let's get to black holes as quickly as we can.
Please,
Skipping over.
Please.
What happened on this day, Jamie? 12th of April.
12th of April, 1961. It's only our man Yuri Gagarin's first flight into space, and that's a hell of an OTD, isn't it?
Well, it's the biggest. It's the biggest OTD, isn't it, that we could possibly have. Vostok 1.
What do you think his heart rate was, Matt, as he was blasting into the unknown?
I'd like to say it was a sort of John Young 68 beats per minute, but I think it probably was a little bit higher than that.
Little bit. Absolutely incredible.
But not only that, what's a really bit of a profound coincidence, because we can't help but mention Charles Messier today.
Oh, yeah.
And he died 202 years ago to the day.
Oh.
He was the French astronomer most famous for the most famous astronomical catalogue there is, the Messier Objects Catalogue.
Yes.
And obviously we're going to get on to M87 when we talk about black holes. And Charles Messier discovered M87.
Oh, he did?
Yeah. Do you know what the whole purpose of the Messier catalogue is?
Go on.
He was a comet hunter, of which he found 13. But one thing that's annoying for comet hunters are nebulous things in the sky, little smudges, because they look like comets. So what Messier did was find all the smudges that are permanently there, all the nebulas. He catalogued them, and that is his catalogue of, you don't have to worry about these because they're not comets.
I love that. So he was discovering galaxies to basically say, it's just not comets. It's just a little smudge.
Exactly right.
Wow.
Very, very important astronomer. Possibly the most famous because everyone refers to the Messier catalogue at all times. But before we get on to more black holes and Messier M87s, we should talk about just a few things that's happening in space.
We should.
We haven't, at time of recording, seen the Falcon Heavy launch that's imminent.
Correct.
So we'll probably talk about that next show. The weird thing is, imagine a Space News week where it's not going to make the headlines.
That speaks volumes, doesn't it, about the kind of week we've had.
A couple of really quick ones. NASA have released the Innovative Advanced Concepts Programme, NIAC. That's really interesting. There's 18 studies that they've picked, which are early stage technologies. Things like, and you'll love this, solar surfing.
Oh, come on.
Materials science study to determine the best protective materials for heliophysics. So in other words, spacecraft surfing around the sun. Solar surfing.
Hell yeah.
You'll love this one. Lunar Polar Propellant Mining Outpost, or the LPMO.
Oh my God.
Affordable lunar pole ice mining for propellant production. And my favourite was the microprobes propelled and powered by planetary atmospheric electricity.
Matt, you are talking my language, son.
I cannot recommend listening to our part 4 of Alan Bond enough, but there's some stuff like that in that. It's on our Patreon feed. Anyone can listen to it. You don't have to be a patron. I just stuck it there because I didn't want it to become a fully fledged episode.
Wow.
Not only
Yeah.
did we get to see a black hole this month, but we also got to see one of my favourite pictures ever. And did you see this? The vapor trails over Norway.
Yeah, ridiculous.
They look like 3 giant jellyfish.
Are you sure they weren't?
I mean, the funny thing is, all these kind of trace sounding rockets,
Yeah.
they're not particularly well, publicised. So it must have been incredible just like looking up one day, trying to see the Northern Lights and seeing them bad boys.
Imagine seeing that. Wow.
I'll put it in the show notes, but the Azure's tracers, so it was a sounding rocket called the Auroral Zone Upwelling Rocket Experiment, or Azure for short.
I just love that. Wow.
So yeah, there's still some really cool sounding rocket experiments that are going on. And that sounding rocket actually was based on the old British sounding rockets from a long time ago.
Oh.
Yeah. So there's
Wow.
a little
the cosmic ballet that goes on.
Goes on, yeah. So a little bit of British heritage.
That was my
in there.
Spock impression.
That was beautiful Spock impression.
Yeah, thanks.
A big one, I suppose, in the old rocket news, as Rocket Lab push ahead of the game. I think they've decided that they're going to start building small satellites as well as launching them.
Go on, Rocket Lab.
Yeah, Peter Beck, talking to The Verge, said, "It always seems bizarre to me that you would have a spacecraft that has all the space components. Is the satellite literally..." No, he's not South African, is he? You do the New Zealand accent.
It always seemed bizarre to me that you would have a spacecraft, that has all the same components as the satellite literally 6 inches away from each other,
But
How was that?
Yeah, that's really good. So
Let me know what you think of that, Kiwis.
yeah, so he's talking about the electron kick stage that takes the satellite into its preferred orbit, and it's just like, well, why bother sort of going through all this rigmarole when we can just build the whole thing? Let's do it. So I think that's fairly major. I think that's kind of sticks them up into a whole new thing. I've got one last
That is major.
piece of space news, which I think would have been the main space news had it not been for all these other things.
Ha! Dream on.
Is yours and my favourite, Hayabusa 2,
Oh, yeah.
carries on delivering, and this time it's fired its small carry-on impactor, the SCI, which is basically a missile that it's fired into Ryugu and smashed up a whole bunch of debris, which a camera that followed it down, the DCAM-3, the DCAM-3, filmed all this stuff pouring out of the asteroid as this projectile hit it. And even more amazing than that is that at some point, Hayabusa 2 is going to lower itself down and scrape up all that stuff that it's ejected out of deeper parts of this asteroid to take it home.
It just blows my mind. I mean, how... I've got so many questions, Matt. Maybe I should save them.
Yeah, and that's the world's first collision experiment with an asteroid.
How good are humans, Matt?
We're pretty good. We're pretty good. And oh, by the way,
And I'm putting myself into that camp too. I know I haven't made any discoveries, but I'm on their side.
I'm interrupting our own podcast because I've just seen that brave little Beresheet unfortunately crashed and created its own little black hole on the lunar surface. Poor little thing. Well done, Space IL. That was still an epic attempt. Keep going. Jamie, we've got a brilliant space fact to finish the show with, so stay tuned. We should just have a space word of the week.
Here we go. Angular diameter. Now, why is this important this week, Matt?
This should demonstrate how absolutely preposterous this whole endeavour was. And you often hear astronomers talking about angular diameter, and I think one of the reasons why it's a common phrase is because if you're not sure how far away something is, it's a bit silly to call it a certain size. So we know how far the sun is away from us, so we sort of give it its actual diameter, right? But if
Yeah.
you don't know how far another star is away from us, because it's quite difficult, then it's better to say its angular diameter. Now, its angular diameter is essentially how much of an angle you'd have to turn your head to look from one side over to the other, right?
Okay.
So if you turned your head all the way round, obviously that'd be 360 degrees.
You'd be an owl.
Yeah, you'd be an owl. But if you looked at one side of the moon and then you have to move your head half a degree to see the other side of the moon, if you were sort of looking absolutely straight, of course, that's a bit ridiculous. Another way to see it, think about it, would be, remember a pair of compasses or dividers that you used to have at school for drawing circles? Imagine if you held that up to your eye and then got the moon in between the two little needles. Then what angle would it be between the two lines of your dividers, your compasses? That would give you your angular diameter, right?
Got it.
But one extra bit of confusion is, for example, when we talk about the moon's angular diameter, you could say half a degree, right? But you can split up degrees into minutes and seconds because, of course, 360 degrees is related to 365 days of the year, etc., etc. So there's a time element in there. So what they do is they split degrees up into minutes. So there's 60 minutes in a degree and another further 60 seconds in a minute. So you can say that the moon is 29 minutes and 20 seconds of angular diameter. You with me?
Imagine if you used that as a chat up line.
Yeah. Well, yeah. I saw you at the...
Hi, love. Did you know that the moon is...
Now, here's a really, really great heuristic or rule of thumb. Literally a rule of thumb for astronomers. Literally a rule of thumb for astronomers. And that is you can vaguely do angular diameter by holding out your hand. So if you hold out your hand as a fist, that, if looking up the night sky, that will give you a 10 degrees of angular diameter, right? Now, if you then hold out your thumb and finger to make it twice as wide, then that's 20 degrees of angular diameter. And then if you have 3 fingers up in the air, that's about 5% of angular diameter. And your little finger, the nail on your little finger is about 1 degree of angular diameter. If you hold up your little finger, you can completely smudge out the moon completely.
Yes.
Which is amazing, isn't it, really, that you think that the moon is only the size of your little finger when you hold it up. But of course, that's
very true.
That's the moon illusion in action for you right there. And of course, things like Andromeda, the big nebula in Andromeda, is actually over a 1 degree. You can't see it because it's so faint and it doesn't have that moon illusion. So it looks much smaller than the moon, but it's actually quite a lot bigger.
Correct.
An arc minute is approximately the resolution of the human eye. So you can just about see 1/60th of your fingernail. That would be, the resolution that you have in your own eye, which is incredible.
What about a New York minute?
A New York minute. What is a New York minute?
Do you remember that song, Matt?
No.
In a New York minute. Ooh.
And what the hell is that?
I can't remember. If anyone knows that band, can you let me know?
Good.
Because I think it was a classic guilty pleasure power ballad, I think.
So 1 arc second, which is 1/60th of the resolution of the human eye, of course, is the same as seeing a coin 2.5 miles away.
Oh my goodness.
Just to give you some example of how small an arc second is. Now, Hubble's Space Telescope can resolve down to 0.05 arc second, although its actual resolution is more like 0.1 arc second. So it can see something 1/10 the size of a coin 2.5 miles away, which is pretty phenomenal. And
that's insane.
And one of the reasons why we had to send a probe to Pluto is because Pluto is 0.06 arc seconds in the sky. So that's 6/100ths of 1/60th of your fingernail. as you hold it up. So clearly you're not going to be able to make that out.
Going back to the black hole, where I saw comments on Twitter of people saying, it's a bit blurry. Why is everyone getting so excited? Where's the 4K version of this black hole? Oh my, can we just try and understand 55 million light years away gargantuan object?
Yeah.
And I don't think they quite understand that it's the same as us trying to look at an orange on the moon. That's what we're dealing with, people.
Sagittarius A star, the massive black hole at the centre of our own galaxy, which is what I thought this photo was going to be of.
Well, they're working on it. I think they're going to get that in relatively short time.
I do.
Because they're actually working on that now.
You know my spreadsheet for different sizes, size comparison.
Oh, yeah.
Right? So if the Earth was the size of a helium atom, right, then M82 itself, the big galaxy, and when I say big, it is absolutely enormous, a supergiant elliptical galaxy, probably made up of lots of other galaxies that have all merged together, and that's why it's lost its spiral structure. If Earth was the size of a helium atom, it would be 25 meters across, but it would be 7,000 miles away. And just to give you how amazing that would be. So if Earth was the size of a helium atom and you've got M87 7,000 miles away and 25 meters across, the black hole that we have pictured would only be 0.004 millimeters across.
Oh my God. Yeah, that's ridiculous.
So do you want to talk about some of the people involved with this breakthrough image?
First up, we've got Shepard and Matt. How am I pronouncing this surname? Is it Doleman?
Let's go with Doleman.
Let's go with that. I'm sure we'll be corrected, but that's okay. Good old Shep. EHT, Event Horizon Telescope Director and Harvard University Senior Research Fellow. And, of course, the name that you'll be hearing a lot in social media is the fantastic Katie Bauman, MIT graduate. 3 years ago, she led the creation of the new algorithm to produce the first ever image of the black hole that we're seeing today. And Matt, have you seen that image of her in front of the dozens of hard drives needed just to form that image?
Yeah, absolutely. So yeah,
spectacular.
Yeah, you can't, as Ethan points out, you can't send that kind of data via Send It or Dropbox.
That's not Dropbox.
No. So my favorite picture of Katie Bauman. Are we going to go with Katie Bauman?
Let's go with Bauman.
Katie Bauman was the picture of her face as the image was revealed on her own computer.
Incredible. And head in hands. Yeah. Who else have we got, Matt?
There's a few ones of note, like Ziri Yaunsi, who's an EHT collaborator from the University College London. And they said the black hole is not the event horizon. It's something inside. It could be something just inside the event horizon, exotic object hovering just beneath the surface. Or it could be a singularity at the centre, or a ring.
Yes.
So this picture doesn't yet give us an explanation of what's going on. And that was followed up by Heino Falk, another scientist from the Radboud University in the Netherlands, said, the big question for me is whether we'll ever be able to transcend that limit. The answer's maybe, maybe not. That's frustrating, but we'll just have to accept it. So yeah, we're still really only seeing the event horizon. We're not actually seeing the black hole.
This is the thing, and I think that it's great actually because a lot of people are now asking questions about black hole online.
So in the images, you can see this clear, bright ring, and the size and the shape and the way that it moves totally agrees with what Einstein predicted all those many years ago.
Wouldn't he be absolutely overjoyed to see that all that hard work was right, and just to see that image? I mean, wow. And Professor Stephen Hawking.
Crikey, yeah. And what's amazing, of course, is it actually ties in with some of the things that we've been talking about. I was actually listening to our own Black Hole episode, Jamie.
Oh, you're so vain.
No, well, I was trying to relearn all that stuff that we dug up from that, and we actually talk about this photograph way back then. It's definitely worth a revisit at that Black Hole episode. It's.
Do you remember the number?
Podcast 71.
Podcast 71.
And I think this is one of those black holes that's so big you wouldn't be spaghettified. You would just drift over the event horizon without even noticing.
Right.
Anyone out there can correct me if I'm wrong on that one, but I think this is one of those just so big that you wouldn't notice it.
Isn't it cool, Matt, that it's not actually a hole?
Don't know what it is.
I mean, I do.
Oh, okay, fair enough.
So, how badass is it that it's so big and its gravity is so vicious, even light can't get out? Can't even imagine that.
There is no direction that takes you out. Space-time has been warped so profoundly, there is no direction out.
If we travelled in our little spaceship up to on the edge of the event horizon, and I jumped out, what would you tell me? What you would see?
If we were on the edge of like M87's black hole, I think what we would see is everyone looking at us. We would just be frozen. But if you jumped past that event horizon, you would be frozen and start slowly fading out. But as you looked out to me, you would see the whole universe's time right in front of you, just going right in front of you. So I mean, it's you can't even begin to imagine what it'd be like. So yes, incredible. Maybe one day we can do that experiment.
I mean, this is so historic, isn't it? This is so historic.
I think we should get on to Ethan now,
I
Jamie,
think we should roll it.
Because he's got some amazing things to say about this. If you don't know who Ethan Siegel is, he has a blog called Starts With a Bang that I followed for a long time, and it's on Forbes. It's now on Forbes.com. He's an American theoretical astrophysicist and science writer. He's a real character as well. What's gutting is that you don't get to see his unbelievable double handlebar moustache and super beard.
Oh, please, can we get a picture up?
Born in the Bronx.
Born in the Bronx. And so Ethan Siegel on Twitter is at Starts With a Bang. So please go and follow.
Yeah, absolutely.
And share in the greatness.
Yeah, definitely check out his blogs and check out his Patreon page as well. Shall we go over to Ethan?
Let's do it.
Good.
The Interplanetary Podcast, putting the ace back into space.
Welcome to the show, Ethan. How are you?
Thank you, Matt. It's my pleasure to be here. I'm doing very well. It's the day before one of the biggest announcements, maybe the biggest announcement that we'll get in all of science this year.
What is it? What's the big announcement?
So the big announcement is there is a worldwide collaboration known as the Event Horizon Telescopes. And for those of you who know that an Event Horizon is more than just a terrible movie from a while ago, Event Horizon is actually what we call the area around a black hole. Outside the Event Horizon, we have things experience all these forces from a black hole, the gravitational force, the accretion disk that'll fry them, the intense tidal forces that'll work to tear them apart through a terrible process known as spaghettification. But inside that event horizon, that is such an area of strong gravitational pull that nothing can escape from it. No particles, no antimatter, not even light itself. And for the very first time in all of history, we are going to be able to image the event horizon itself. We're going to see that region from within which light cannot escape. And we're going to see that very first image tomorrow at, I believe it's just at 2 p.m. GMT.
Well, have you got any idea what this image is going to look like? Because obviously we've been exposed to hyperreal images of black holes, and especially things like Interstellar and stuff like that. What kind of thing can we expect to see?
Well, Interstellar is a pretty good depiction of what a specific type of black hole will look like with an accretion disk around it. What you have to recognize is the biggest black hole, as seen from Earth, is the giant black hole at the center of the Milky Way galaxy. It is 25,000 light years away. But it's, in terms of physical diameter, it's only somewhere around the size of like Jupiter to Saturn's orbit in our solar system. So imagine that you had an object that was that physical size, the size of maybe Saturn's orbit in the solar system, and you wanted to see it, you wanted to resolve it from 25,000 light years away. That is incredible. In astronomy, we talk about angular sizes, like, oh, I know you're probably familiar with the concept of degrees, where if you held like your thumb up at arm's length and you said, how big is my thumbnail? Your thumbnail's about 1 degree. So now take that 1 degree, divide it up into 60 equal pieces. That's an arc minute in astronomy. 60 arc minutes make 1 degree. Well, take one of those arc minutes, divide it up into 60 arc seconds. That's 1 arc second. When we're talking about the physical angular size of this black hole on the sky, we're talking about something like, I want to say about 30 micro arc seconds, which is to say that imagine taking this tiny, tiny fraction of your thumbnail, this 1 arc second. Now take 1/30,000th of that. That's about the size of the black hole we're looking at. So if you're expecting this big, spectacular, high-resolution image, you're going to be disappointed. But what we should be able to see reconstructed is this image that's maybe 2 or 3 pixels of blackness across it where no light escapes from it, surrounded by a bright radio-rich region. We're looking at this with radio telescopes because we know accretion disks, they're made of matter. Matter is made of protons, neutrons, and electrons. When charged particles move around, they create an electric field. And when charged particles move in an electric or a magnetic field, they emit radiation. And that radiation is what we can observe in radio wavelengths. Because we've set up a network all around the world of radio telescopes that are looking at this simultaneously, we can actually resolve a place where there's no radio emissions separate from the radio emissions around that event horizon. So that's what I would expect to see. Is I would expect to see this like ring of radio emissions surrounded by blackness on the inside. Perhaps it'll be brighter on one side because when things spin around, one side's coming towards us and one side's moving away from us. So we expect that one side might be brighter, and there might be a little bit of radio emissions coming from in front of it where the disk crosses in front, just because if you were imagining, let's look at the planet Saturn, and imagine that the planet itself, that big spherical disk of a planet, was all blacked out. But you'd still be able to see the part of the rings that were not only on the sides of Saturn, but the part in front of it. That might be what I would expect to see from the Event Horizon Telescope when it releases its first image tomorrow.
Wow. I mean, I know that it's going to blow my mind. I always worry things like this, that there's going to be this huge expectation to see something absolutely spectacular. And like you said, it's going to be a few black pixels. It's a bit like when they show you the furthest galaxy that they know, and it's really just a red pixel on a star field. But it's
right.
But
that's a great analogy. That's absolutely right. Because, you look at it visually and you're used to seeing either these incredible Hubble images of these close by objects where you're seeing them up close and you say, wow, look at the resolution on that. It's absolutely incredible. But you're also saying, okay, well, why isn't my image like this? And for the farthest galaxy, you're saying, oh, it's because you're looking at something from, 97% of the universe ago to when it was just 400 million years after the Big Bang, and the universe had to send that light all the way throughout the universe. And you're seeing it now, and you're complaining like, why doesn't it look prettier? And you're like, oh, come on. Can't you just be so grateful for all the incredible work that went into creating this image, the technology that we had to develop in order to see it at all, and all of the amazing physics and science and astrophysics that we can learn just from making these observations? For me, the biggest revolution of this is anytime you get to take your most fundamental theories about the universe, something like how does the universe work on this fundamental quantum level, or what's the most fundamental force we know of, it's gravity, and how does gravity work at a fundamental level? When you get to test that in a whole new way, when you get to push the frontiers, you open yourself up to two big possibilities. One is that we will confirm our most deeply held theories about the universe to a greater precision than ever before. The other is there's a possibility that we'll see something unexpected. And when that's what you get, when you see something unexpected about the universe, when you're testing it in a whole new fundamental way, that's a chance for a revolution in physics. Now, I'm not expecting general relativity to be proven wrong, but I am expecting a remarkable test of general relativity that will reveal new information about black holes, how they work, how accretion disks work. We're going to see a whole lot of firsts with this, and that's always incredibly exciting, regardless of what it reveals.
No, absolutely. So one of the reasons why a lot of scientists are getting very excited about the whole announcement is that up until very, very recently, everyone thought that this was an impossible task to take a picture of the black hole at the center of our galaxy. Why did it seem so impossible a few years ago, and what's changed to make it possible now?
Okay, so we're going to get a little bit technical, but I'll try and keep it in accessible terms, in as accessible terms as possible. I already tried to impress on you how tiny on the sky this actually is. This black hole event horizon actually is. For comparison, if you wanted to take a look at the nearest star to Earth, and you said, oh, maybe there's an Earth-like planet orbiting the nearest star. And you say, yeah, maybe there is. Let's say I want to block out the starlight from the actual star and just image that planet directly. We are a long ways away from actually being able to make that image. And even if we did, that image requires a resolution that we would measure in milliarc seconds, not micro arc seconds. So we're talking about doing a type of observation that's literally hundreds of times higher resolution than an observation that we'd love to and can't even make with today's technology. So when you say, well, what determines that resolution that I can get down to? Normally, it's the size of your telescope, the physical size of your telescope. You might remember learning that light is a wave, that light waves have a certain wavelength, and that wavelength determines what the energy of that light is. So at very short wavelengths, you have things like gamma rays and X-rays, and at long wavelengths, you have things like infrared and microwave and radio waves. Radio waves are the longest. Now, radio waves are great for looking at, say, the center of the galaxy, because all of the dust and stars, and, if you've ever seen the Milky Way, which I don't imagine you get to do very often in the UK, but you can in many places across the world that are preserved dark sky sites. So if you get to see the Milky Way, you will notice that it will look like it's this giant white diffuse cloud that spans the whole sky, but it's peppered with these dark black streaks. Those black streaks are dust and they block the light. If you were to say, I want to look at the galactic center in visible light, you can't see it because there's stuff in the way. But at longer and longer wavelengths, in the infrared, in the microwave, and most importantly in the radio, all of that dust is transparent to light. So if you looked in the radio portion of the spectrum, you will be able to see what's actually going on in the center of the galaxy. The problem is your resolution is determined by the number of wavelengths that fit across your telescope. If you wanted to build a single telescope that was able to resolve the event horizon in radio wavelengths at the center of the galaxy, at that giant black hole, you would need a telescope almost the size of planet Earth. And obviously, we do not yet have the technology or the real estate, for that matter, to say, hey, it's for science. Can we just have like half of planet Earth to build a radio telescope on it? I imagine that there would be about 80 or so countries, no matter where on Earth you chose to build it, that would say, yeah, no thanks. No thanks. We're going to keep our nation. Thank you. So how does the Event Horizon Telescope do it? Well, it uses this incredible technique known as very long baseline interferometry. And the 15-second version of what this technique does is it basically says we're going to take a network of radio telescopes and we're only going to get the light gathering power of each of these individual radio dishes. But because of the way we're working together to take these observations simultaneously, where we're locked, where the telescopes are locked across Earth, we're going to be able to get the resolution of the distance between the telescopes, even though we're only getting the light gathering power of the individual dishes themselves. So that's how we can cheat this property of telescopes and make an effective telescope to give us that ultra high resolution. The cons are, it means we can only observe the extreme brightest things, but the accretion disk, the radio emissions around a black hole, are that thing, are that exciting thing. So that's why this is such a big deal. And the reason we couldn't have done this 10 years ago, even 5 years ago, is because there's this enormous radio telescope array that exists on the South American continent known as ALMA. It's the Atacama Large Millimeter Submillimeter Array. And this is a network of about 60 or 70 ultra powerful radio telescopes that are scattered across the South American continent. When we combine that with radio telescopes elsewhere in the Americas, like in North America, and on the African continent, and in Europe, and in Antarctica, and maybe even in Asia, and we add them all together and we say all of these telescopes, including the one at the South Pole, are all working together to make these observations. That's how we do it, with simultaneous observations, that we bring this data together, and then all the astrophysicists who work on analyzing this data can clean it up and sync it up and look at the atmospheric conditions at each of these places and correct for them and bring these observations together. All told, they have to sift through about 27 petabytes of data. And for those of you who don't know what a petabyte is, it is 1,000,000 gigabytes. 1,000,000 gigabytes is 1 petabyte. So you have to sift through 27 petabytes of data to pull out about the 4 or 5 petabytes that are useful. And then, bam, then you can do it. Then you can go ahead and say, perfect. Now, at long last, I can go and analyze all this data across all of these telescopes, synthesize them together, and try to produce an image of a black hole's event horizon.
Wow. Yeah, I mean, so we've got this absolutely monumental, and when you put it like that, you realize just how fantastic science is globally in terms of these kind of monumental events are such global efforts involving many nations, many scientists, lots and lots of money.
It's no exaggeration to say that there are thousands, probably tens of thousands of scientists, if you include everyone who took the data, built the telescopes, operated the telescopes, brought the data together, and then analyzed the data in the data centers that were built explicitly for this purpose. A lot of people were like, have been asking me, and I've been asking a lot of people since 2017, so when are we going to see that first image of a black hole's event horizon? Because the truth is, we took all of this data 2 years ago. We've been sitting on this data since about April of 2017. Well, we had to bring the data physically from Antarctica to another place. You can't very well go and I don't know, Dropbox a few petabytes of data from Antarctica. You have to physically bring the drives together. And then you have to analyze them, and you have to see what are all of the unknown signals and complications that come up when you take this data of a type we've never taken before for the first time. A lot of people are going to be disappointed and say, oh, we could have seen this image, 18 months ago or 12 months ago or 6 months ago, if only they had gotten their act together faster. But this is the amount of time it takes to get it right. Nobody wants to see an incorrect image or an image riddled with errors because they didn't reconstruct it properly. Science, big part of science that is often underappreciated is how much care you have to take to ensure you've caught all the mistakes, you've caught all the errors, you've corrected for everything you can possibly correct for. And now, at the end of the day, you have the correct answer. You have the best image you can construct based on the data that you've acquired.
So this huge data set that was gathered was imaging a black hole for the first time its primary purpose, or are these data sets actually contain a lot more detail about the universe, and they're working on multiple problems at the same time?
Well, the black hole at the center of our galaxy is a really big deal. This was, I would say, the Event Horizon Telescope's primary mission is to take this image, construct this image of this particular black hole. But also, you have to realize that this is not the only black hole that the Event Horizon Telescope is going after, and this is not the only target for very long baseline interferometry. So, for example, the ALMA array, the Atacama Large Millimeter Submillimeter Array that I told you is the big advancing thing that allows us to say, oh yeah, this is what allows us to view the event horizon itself. ALMA's been at work viewing incredible things in the distant universe, other than event horizons of black holes. It's been viewing these little tiny protoplanetary disks that form around newborn stars. It's been able to see gaps within the disk that we think correspond to the locations where the very first seeds of planets are forming. We may be looking at the evidence for infant gas giants or infant Earth-like planets in the disks of these stars. ALMA is able to probe the interstellar medium like never before and say what's going on in the depths of interstellar space. We have a saying in astronomy that a lot of people, don't like anymore, but it's still true, which is that one astronomer's noise is another astronomer's data. So you can look at black holes and say, oh, I'm not interested in the black hole itself. I'm interested in the radiation from around it. Or you could say, oh, I'm interested in not seeing through this dust in the galaxy, but I'm interested to know, how does this dust change the light that's arriving at our eyes? Some people are actually interested in the atmospheric effects. But it's worth pointing out that there's another black hole that's extremely different from the one at the center of our galaxy, that if we're very lucky, and we might get lucky, it's conceivable that we will actually get a second image from the Event Horizon Telescope, because farther away, about I want to say about 20 to maybe 24 times farther away than the black hole at the center of the Milky Way, is a black hole at the center of a galaxy known as M87 or Messier 87. This is the largest black hole within something like 200 or 300 million light years of Earth. There's a large cluster of galaxies known as the Virgo cluster. And this is a cluster of galaxies. Our local group has a Milky Way, has Andromeda, and maybe 60 other dwarf galaxies, other tiny galaxies that are much, much smaller than the Milky Way or Andromeda. The Virgo cluster of galaxies has about 1,000 Milky Way-sized galaxies or bigger inside of it. And this is the largest cluster of galaxies in proximity to where we are in the universe. The largest galaxy there is M87. And instead of having a black hole of an estimated 4 million times the mass of the sun, it has one that's about 6.6 billion times the mass of the sun. And just so everyone's aware, those are United States billions, where I mean 6.6 times 10 to the 9, or 6.6 thousand million times the mass of the sun. That is enormous. It should have an event horizon that's probably about 2/3 the size of the Milky Way's event horizon. So there's a chance that the Event Horizon Telescope will actually be releasing 2 images of event horizons tomorrow. Now, I'm betting on the one closest to us and not the other, because, you never know. But who knows? Maybe we'll get really fortunate and we'll actually see that second black hole as well.
Wow. Yeah, I didn't know anything about the second black hole. That's really exciting. I've actually managed to image M87 from my back garden. That's in London, but and even the Milky Way. You'd be surprised in the UK. I happen to have moved near a dark sky site now, so I do get to see the Milky Way. That's
okay.
Yes.
No, that's great. Like I would be surprised, but this is a pleasant surprise.
Yeah. It's good. It's there's some good places still, just about. But yeah, we're pretty badly light polluted here. One question I do have to ask: we've got this absolutely monumental effort, obviously, into going into this kind of science, into cosmology, etc., etc. For the average person looking on, why does it matter to them? What can you give a good speech about why this is important, really, for humankind, I suppose?
Sure. So you might have said 100 years ago, okay, so Newton's gravity is pretty good, and we use it for all the things we can imagine wanting to calculate, gravity on Earth, gravity near Earth, etc. Why would we care about this subtle difference in gravity that shows up when you get very close to very large masses, like general relativity offers over Newtonian gravity? Why should we put all of this effort into, testing out which theory of gravity is right, into pushing the limits of what's fundamental? Why should we pour all of the UK's resources into the Eddington expedition of 1919 that goes and tests Einstein's general theory of relativity with a total solar eclipse? Why should we do any of that? And 100 years ago, you would have said, I don't know what's going to happen. I don't know why I should care about this, because you wouldn't have anticipated a whole slew of very important aspects of modern life, like GPS, like atomic clocks, like a space program, like, you wouldn't have anticipated any of these technologies. And so you would have said, oh, well, I can't even see why it's important to know how good our theory of gravity is. Well, guess what? This is the next frontier. We are saying when we make these observations, we are putting general relativity to the test as never before. We are learning more about our universe in a fundamental way than we've ever known. And we're asking a new type of question in a new way that's going to enable us to learn information we couldn't have gotten otherwise. So one of the big things we're going to learn is, do black holes have the correct sizes that general relativity predicts? According to Einstein's theory, we've got a certain prediction for the size of the event horizon, and therefore, related to that, we've got a prediction for what we should see as far as the dark spot coming from the event horizon itself. It's slightly different, but with its incredible resolution of just 15 micro arc seconds, the Event Horizon Telescope should be able to see a horizon and measure, does that size match our predictions or not? It will be a fabulous test of general relativity. We're also going to learn some amazing things about black holes and accretion disks and galaxies. Are they aligned? Are they aligned? Are the accretion disks aligned with the black hole? Are they aligned with the host galaxy? Or are they randomly aligned? We've never observed a black hole's accretion disk before. And this could tell us a lot of information about generic phenomena that happen in the universe. These aren't just esoteric questions about black holes. These reflect things we could someday use as far as a galactic network of clocks or a galactic map of what's out there, or understanding how these objects evolve over time. You might say, oh, well, we're not doing interstellar travel yet, so why should I care? And I'll say, give yourself something to dream towards. Give yourself something to work towards. We don't even know if a black hole's event horizon is circular as predicted, or if other shapes are possible. Some objects like planet Earth that spin bulge along their equators when they rotate. This is a shape like an oblate spheroid. Could a black hole actually have an oblate spheroid shape? Well, if general relativity is correct, a sphere will be what we anticipate, but there's no substitute for making those observations yourself. We might also get to see from future observations of the event horizon where you're detecting changes in the emissions around a black hole over time. Hey, why do black holes flare? When it's in a non-flaring state, there are specific signatures that we expect to get around the event horizon, but when it does flare, there are different features we expect. Will there be turbulent features? Will there be hot spots? Will we learn why black holes flare just by looking at these extended radio emissions? Boy, I bet you want to know. We have somewhere around more or less 1 billion black holes in the Milky Way galaxy. If we wanted to travel the galaxy or probe the galaxy or measure the galaxy, boy, it sure makes sense to understand these massive, dense objects that there are a billion of out there. We're also going to learn things that are just really important for astronomers to know. For example, if I take a look at the stars that orbit this super massive object, I can say, oh, well, I know how gravity works, and I get an estimate for the mass of the black hole by looking at how these stars are moving throughout space. And I say, oh, yeah, I get a mass of around 4 million solar masses for the black holes. But if I look at the gas that emits X-rays from near the black hole at the center of our galaxy. And by the way, X-rays are way easier to measure than individual stars moving in orbit thousands and thousands of light years away. I can say, actually, the mass estimate I get from X-rays are about a third smaller, about 2.5 million solar masses instead of 4 million solar masses. Well, guess what? X-ray observations are how we infer the masses of most black holes beyond our galaxy. Does that mean the X-ray estimates are biased? Does it mean something is wrong with our gravitational observations? Guess what? The Event Horizon Telescope is going to teach us how to discriminate between these two. The size of that black pixel area we're going to get is going to tell us whose mass is right. Are the X-ray masses right, or are the gravitational masses right? And if something is wrong, it's really important to know which one is wrong and how is it wrong, so that we can better understand the way the universe works. And one thing that I think is really exciting is we're going to be able to construct these images over time. You know that, the planets all orbit the sun, right? But you also learn that for every action, and action in this case means force, there's an equal and opposite reaction, or force. So when the sun pulls on Earth, the Earth pulls back on the sun. When the sun pulls on Jupiter, Jupiter pulls back on the sun. If you were to measure the sun over long periods of time, you would actually start to see that the sun jitters in space because of the planets that cause it to move. Well, guess what? At the centers of galaxies, these supermassive black holes are going to have that same jitter, not only because of the stars that orbit them, but because of smaller black holes that we can't resolve. We're going to actually learn how full of black holes and what types of black holes and what masses of black holes the center of our galaxy is full of, just by continuing to make the same types of observations that the Event Horizon Telescope is already making.
This is really, very, very exciting. So in some sense, we're hunting down dark energy and dark matter. Will this kind of process help that process of hunting down all the bits of knowledge that we are clambering around for at the moment?
I think it's important to be clear about what sorts of projects it will and won't help with. Right now, observing black holes in our own galaxy won't really help us with dark energy. If you want to understand dark energy, it really only affects the universe on the largest scales, on scales where something isn't bound to us. So if I were to make a measurement here on Earth, well, the Earth and everything on it is a bound system. Dark energy doesn't affect it. This is true within our solar system, within our galaxy, and even within our local group. But if you start measuring signatures outside of our galaxy, that's how we discovered dark energy, is by looking at distant observations, distant objects, and seeing how they're different and how their light is changing as it travels through the universe towards us. Well, as we start to improve on the Event Horizon Telescope and measure more and more black holes at greater distances in different clusters of varying masses, that might be a prospect for starting to test dark energy in a new way. As far as dark matter goes, black holes are a form of dark matter, but we know they cannot be all of the dark matter. What we might be able to do, however, is start probing things about dark matter from looking at these very rare but very real cases where you have two supermassive black holes orbiting each other in the same galaxy. And you say, oh, wow, that seems super unlikely. And I'll tell you, well, we know of one. If I tell you, I'll just tell you to plug it into Google. These 5 characters, OJ287, and put a space between them. OJ287. That is a binary black hole system where one of the black holes is enormous. It's more than 10 billion solar masses. It is bigger than even the black hole at the center of M87. But there's also a second very, very massive black hole of about 150 million solar masses that orbits that black hole. You have 2 black holes in orbit around one another. In general relativity, we thought it was a big deal that we could say, actually, the way Mercury orbits the sun isn't a perfect ellipse, that every century, Mercury's orbit precesses by an extra 43 arc seconds, almost one whole arc minute every century. If you were to look and say, oh, how much do these black holes in OJ 287, how much do they precess? If you were to look at it in terms of a century, it would be almost a full circle, almost a full 360 degrees, because general relativity's effects are so pronounced there. So if you're looking at systems like that, you're really saying, you know what, I'm able to test the universe in a whole new way. Dark energy, maybe, but if I start getting large numbers of these systems, maybe I can start learning something about dark energy, because I could see how these radio emissions change over time differently in different galaxies and galaxy clusters at different distances. Maybe I can learn something about dark matter by looking at the distribution of these black holes that are present in large clusters. So they do offer a potential way to explore them, not with the initial observations, but maybe down the road. It's important to remember that science is a process that the body of knowledge builds upon itself. When Newton says, oh, if I see farther than any man before me, it's because I've stood on the shoulders of giants. I can't say the word shoulder right now, on the shoulders of giants. He wasn't just taking a dig at the short, hunchbacked Robert Hooke. He was taking a long view of things and saying, you know what? I see farther than those who came before me because I can build on their work. We can see farther than Newton did, farther than Einstein did, farther than Hawking did. A lot of people will lament, oh, we've already discovered so many things. It's a terrible time to be alive and a scientist. I disagree. This is the best time because we know more than we've ever known before, and we're pushing frontiers that generations ago we could only have imagined.
Yeah, absolutely. I couldn't agree more with that. And one thing, reading your blog, definitely you get over that sense of excitement and everything that's happening in science at the moment. I'm actually thinking that it's one of the most exciting times ever, and it seems to me there's a general excitement in science. And so many discoveries in the last 10 years, like gravitational waves and the Higgs boson, and now photos of black holes and things like that. And you think this is incredible time to be alive. Absolutely.
I absolutely agree. And I think as far as physics and astrophysics goes, those three discoveries, the Higgs boson, gravitational waves, and the image of a black hole's event horizon, I think these are probably the three greatest discoveries of the entire decade. And I can't wait to actually get my eyes on that image tomorrow, and hopefully a few hours later to start sharing with the world the story of what it actually means and tells us.
Fantastic. Well, on that note, where can people read what or hear or see what you have to say?
Sure. My blog is called Starts with a Bang. I've been writing it since 2008, and I've written, thousands and thousands of articles for it. It's currently hosted at Forbes, so you can find me at forbes.com/sites/startswithabang. I'm also on Patreon. So Patreon supporters, if you want to throw a dollar or two my way or a pound or two my way to say, hey, I want to see all of Ethan's articles, but I want to see them ad-free, and I want to see them where it's just me and a few other supporters, and I want to know what's going on with him and what he's doing to help bring more science stories to the world. You get everything first run and ad-free. You also get input on, what it is we're going to be choosing to write about or study. We do podcasts once a month. Those of you who are either on SoundCloud or in the iTunes store, you can look for the Starts with a Bang podcast. And you can find me on Twitter, Facebook, Tumblr, and all sorts of social media as Starts with a Bang.
Excellent. And I noticed actually you're very, very close on your Patreon page to one of your first goals. So that's definitely a good place to go, I reckon.
I think I'm plowing ahead and I'm trying to tell the stories of the universe, to as wide an audience as possible in as many formats as possible, but also to tell people what it is we know and how we know it, to give you the full story behind things. So you're not just getting a pretty picture or a layperson's redux. I think that people actually crave and hunger for the real story that isn't, dumbed down or put in simple terms. People want the full story in as simple terms as possible. They just don't want the equations with it. They don't want the details, the esoteric stuff, the jargon. Can you break it down in plain language so that anyone can understand it? That's what I'm trying to do in as many formats as possible. And anyone who supports me, I'm just super grateful that you believe in me and you believe in what I'm doing and you want more of it to happen.
Well, I can't recommend your blog starts with a bang any more than that. It's absolutely fantastic. I've followed it for a long time, and it's really, really great. And I have to say, I'm going to make the listeners slightly jealous in the fact that for this entire interview, I've been able to see a very animated Ethan and an unbelievable moustache and beard. It's very animated and brilliant delivery of all the material. So thank you very much for coming on the podcast, Ethan.
It's been my absolute pleasure. Thanks for talking about all things science with me, Matt. And it's my pleasure to contribute to the Interplanetary Podcast.
The Interplanetary Podcast is alive!
So what do you think about that one, Jamie?
Yeah, just mind-blowing. And in fact, I am currently staring at his Twitter page, excited to, after we finish this podcast, Matt, his latest tweet, 10 deep lessons from our first image of a black hole's event horizon. So Go and have a look at this. It will put some refreshers in there of what you just heard.
It will carry on the journey.
It will.
Absolutely. Jamie, I've got a space question for you as our space fact.
Go on.
Do you think the Earth is gaining weight or losing weight each year? Because we've had a few things, haven't we? Because we were talking a few weeks ago about how Earth gains about 40,000 tons of space dust.
Yeah, that's right.
Year.
I was going to say it's the space dust and the amount of debris that falls into Earth. So I would say gaining, very much gaining.
Okay, but also the Earth gains weight because of global warming. Did you know this? So obviously,
I didn't know this.
E equals mc squared. So as the global temperature goes up, so does the mass.
Oh, okay.
because mass is energy. Oh, by the way, that gain is about 160 tons of matter a year in global temperature.
Oh, Lord.
In terms of Earth's core, though, that's cooling down by about 16 tons every year. But the biggest loss is 95,000 tons of hydrogen and 1,600 tons of helium escaping because of they managed to get to escape velocity and are lost to the Earth forever every year. So actual fact, really, we're losing weight by about 50,000 tons a year.
Well, look how good we look.
Yeah, and the reason why I looked this up, Jamie, is because I heard a fact the other day. You know about the Chicxulub asteroid that wiped out the dinosaurs, or is believed to have wiped out the dinosaurs, right? 65 million years ago, it hit the Earth and wiped out 99.9999% of life on Earth, or 87% of the species on Earth were wiped out. There have been some amazing finds relating to that in sediment and things like that quite recently. But one of the things I didn't realise is that impact launched about 70 billion kilograms of rock into space.
Oh.
70 billion kilograms of rock into space.
Yeah, that is going to shed some weight.
Yeah, so that actually makes all the other stuff seem quite small. So it's a huge amount. But get this, 20,000 kilograms could have got as far as which of your favourite bodies in the
Europa.
Europa.
Oh my God! Wait, are you talking about reverse panspermia?
Yeah. I am talking about.
Holy-
So if we do
Holy
find
shit.
if we do find microbes and stuff on Europa, there is a huge chance actually that a big enough
That they
rock
came from us.
Yeah, that a big enough rock that could have protected like microbes in its core as it journeyed through space could have literally have landed on Europa and seeded microbes
So
there.
are you saying that there potentially could be swimming pterodactyls on Europa that evolved from microbes smashed out of Earth's rock?
I'm going to say yes.
Are you saying that to me?
I'm going to say
Yes or
'cause-
no?
I'm going to say yes, Jamie, because I want them to finish this podcast on a massive high for you.
Oh my God. Okay, I read you. So Matt, 55 million light years from M87 and its supermassive black hole that we discovered yesterday. So what would have been around on the Earth at that time? Just a few animals? Or when I say a few, I mean obviously more than a few, but a lot had already been wiped out.
Yeah, well, that's only 10 million years after that impact. So yeah, we probably were quite sparse. They would have
Quite sparse, yeah.
Quite sparse. I mean, we would have had a very similar fauna as we've got now. Basically, the dinosaurs will have been wiped out, and mammals would have started their rise. So yeah, it's a very similar time period, isn't it? Really.
Well, Matt, on a little bit of a tangent, did you see that this week another big discovery that they found a new species of human
I didn't see
with
that.
with curved fingers and toes in a little on an island in the Philippines, and so they believe that they were big climbers because of this DNA that they found in the bones.
Wow.
Amazing.
I tell you what.
there we go.
I tell you what's a pretty big coincidence about Messier 87.
Oh yeah.
Which could have been the space fact of the week, is exactly 100 years ago in 1919. There was a supernova in M87 that reached a magnitude of 21.5. That's a very bright.
That is bright.
That is a very bright supernova, and it was almost not discovered until a Russian astronomer, Inokentil E. Belanowski, discovered it in photographic plates in 1922. So amazing, 100 years ago today to a massive supernova in M87 that we could see. So again, it's like that supernova happened when life was just starting to get going again on Earth.
My God. You know when sometimes bad news gets to you, Matt, and you feel like you can't take any more? Well, I feel like I've had too much good news.
Yeah, it's an amazing
I don't know
time.
what to do with myself.
What a great time to be alive.
What a week.
We better go, Jamie, and let these other
We'd better
human
go.
beings get on with their week.
Yeah, let's say goodbye. So, Matt, I'm off to check out the size of my singularity. What are you up to?
I'm tiling my floor despite the beautiful sunshine outside. I've got to get on and finish this house off.
Well, get yourself grouting, boy.
Aye.
All right, my little M87 fans. Have a good weekend.
Bye-bye, Spodcat. See you
See you
next week.
Bye.